So I want you to picture a scenario for a second. You're driving down the highway.
Okay.
It's a beautiful, completely clear day. You're behind the wheel of this really high-performance electric vehicle, just cruising at, 75 miles per hour.
Right, just a normal road trip.
Exactly. The ride is incredibly smooth. The cabin is quiet. Everything feels perfectly engineered, like you have complete control.
Sure.
And then in literally a fraction of a millisecond, the vehicle's central computer totally loses track of the physical position of the motor's spinning rotor.
Oh, man. It just goes blind.
Completely blind at 75 miles per hour.
Yeah, the computer loses the one piece of physical reality it actually needs to drive the car.
It's a terrifying scenario if you stop and think about the physics involved. I mean, we are talking about a 2-ton piece of metal moving at high velocity, and it's relying entirely on a magnetic field to govern its momentum.
Right, and for the engineers who design these vehicles, preventing that exact loss of control, I mean, that is the thing that keeps them up at night.
So today, we're taking a massive deep dive into this brilliant technical document we have. We've got a source here titled Rotor Position Estimation Failure Analysis and Safety Protocols.
And I should warn you, this document is heavy. It isn't just a standard maintenance manual.
Oh, not at all.
We're looking at the foundational architecture of an ASIL D failure protocol.
And for anyone not deeply embedded in automotive engineering, ASIL stands for Automotive Safety Integrity Level, right?
Yes. It's a risk classification scheme,
Mm-hmm.
and the D level is the absolute highest, most stringent tier possible.
Like the ultimate worst-case scenario rating.
Exactly. It's reserved for hazards that carry the highest potential for severe, life-threatening injuries if they aren't handled perfectly.
So our mission for this deep dive is basically to act as engineering detectives.
I like that.
We're going to unpack this incredibly complex core failure, the rotor position estimation failure. We're going to translate a lot of dense multi-physics into concepts that you can actually visualize.
Because there's a lot going on here.
So much. We'll look at the underlying physics of how things break, the real-time software diagnostics that catch those breaks, the proactive design measures engineers take, the manufacturing controls, and the brutal physical validation testing.
I am thrilled to get into this. Because this specific failure mode, the position estimation failure within a dual motor controller, it's widely considered the most technically challenging multi-physics problem in the field of functional safety right now.
Wow, the most challenging.
Yeah. We're not just talking about a simple software glitch or, a loose bolt. We're talking about the intersection of semiconductor physics, electromagnetic interference, advanced algorithms, and literally microscopic material science.
Well, let's start right at the beginning then. Before we can appreciate the brilliant ways the vehicle saves itself, we have to understand the anatomy of the glitch.
Right, how it actually breaks.
Exactly. We have to understand how the position estimation actually fails. And the source makes it clear that it's almost never just one isolated event.
No, it's a chain reaction.
So the first major mechanism the document outlines involves silicon carbide and something called common mode to differential mode conversion.
To understand this, we need a quick primer on what the heart of a modern high-performance EV inverter is actually doing.
Okay, lay it on us.
So, the inverter's job is to take direct current, DC power from the battery and chop it up into alternating current, or AC power, to feed the motor.
Right.
And to do this efficiently, modern EVs use silicon carbide, or SiC MOSFETs. These are essentially incredibly powerful, highly efficient electronic switches.
And they represent a massive leap over older silicon technology, right? Because they handle more heat and operate a lot faster.
Way faster. They switch on and off at speeds that are almost hard to fathom. We're talking about generating voltage change rates, what electrical engineers call DVDT, of over 10 kilovolts per microsecond.
Let me just put that into perspective for you.
Yeah.
That means the voltage is swinging by 10,000 volts in 1/1,000,000th of a second.
Yeah.
That is a violent electrical transition.
It's incredibly violent, and physics demands a toll for that violence.
It always does.
When you switch voltages that high, that fast, you generate an immense amount of high-frequency electrical noise. This is called common mode noise.
Okay, so you have this noise storm.
Right. And because of the physical layout of the motor, this noise easily propagates through the parasitic capacitance of the system.
I just want to pause on parasitic capacitance because that term sounds like a sci-fi villain.
It kind of is, honestly.
In electrical engineering, Anytime you have two conductors separated by an insulator, you inadvertently create a tiny invisible capacitor, right? A device that stores an electrical charge.
Exactly. You don't build it on purpose. It's just a physical parasite of the design.
So you have this massive noise jumping across these invisible energy bridges. How does the car's computer actually deal with it?
It relies on a very specific filter. The motor has a sensor called a resolver, which acts as the computer's eyes. It tells the computer exactly what angle the spinning rotor is at.
Right, so the computer knows where the physical metal actually is.
Yes. And to protect the delicate signals coming from that resolver, engineers build an analog front end, an AFE. This front end uses a perfectly symmetrical RC filter, resistors and capacitors, to catch and suppress that high-frequency common mode noise before it reaches the digital brain.
The key word there being symmetrical, because the source material really emphasizes how fragile that symmetry is.
Highly fragile. Imagine the physical resistors and capacitors on the circuit board. If there's even a microscopic manufacturing tolerance difference between them.
Or thermal drift, right. The physical heat of the car changes the electrical resistance slightly.
Exactly. If one side experiences thermal drift, that perfect mathematical symmetry is broken.
And when the symmetry breaks, the filter doesn't just stop working, it actually makes the problem worse.
That is the insidious part. That asymmetry takes the common mode noise, which is normally relatively harmless because it affects both signal wires equally, and it forces a conversion.
It changes it.
Right, it turns it into differential mode noise.
Which is the worst possible outcome. Because the actual vital data coming from the resolver, the sine and cosine waves telling the computer the angle, those are differential signals.
So this new chemically altered noise gets perfectly superimposed directly on top of the delicate resolver signal.
Okay, I have an analogy to help visualize this.
Let's hear it.
Imagine you're trying to listen to a very important whisper from across a room. That whisper is the resolver signal.
Okay.
But outside the building, someone is blasting a foghorn. That's your silicon carbide switching noise. Now, normally, your brain can tune out the foghorn because it's just a constant background drone hitting both of your ears equally. You filter it out.
Right, common mode.
But let's say the room you're in is totally asymmetrical, with weird acoustic angles. That foghorn noise bounces off the walls, changes its acoustic profile, and suddenly it's funneling directly into one of your ears at the exact same pitch and volume as the whisper.
It completely swallows the truth of the whisper.
Exactly. It drowns it out completely.
That illustrates the problem beautifully. The noise bounces off the electrical asymmetry and swallows the physical truth of where the rotor actually is.
And once that signal is corrupted by the noise, we hit the second link in the chain reaction, right? The resolver to digital converter, or RDC chip, has a complete meltdown.
It does. The source gets very specific here, mentioning chips like the AD2S1210.
Right. And these chips use a Type 2 angle tracking observer and a second-order phase-locked loop.
Yeah, the phase lock loop, or PLL, is basically the internal logic trying to stay locked onto that whisper we just talked about.
And the document outlines 3 fatal failure modes for this chip when things go wrong. LS, DOS, and LAW. Let's break those down. What's LOS?
Let's start with LOS, which stands for loss of signal. This is a very physical problem.
Because of heat, right?
Yes. As the motor runs, it generates heat. The copper wire is carrying the signal heat up alongside it. And physics dictates that as copper heats up, its electrical resistance increases.
The source notes a temperature coefficient of positive 0.393% per degree Celsius?
Right. So if the motor is pushed too hard and gets too hot, the physical signal strength pushing through those increasingly resistant wires drops.
So the whisper is getting quieter and quieter because the air in the room is getting thicker?
Exactly. And the chip has a hard-coded threshold. If the differential peak-to-peak voltage falls below, say, 2.00 volts, the chip simply gives up.
Just throws its hands in the air.
In just 5 microseconds, it triggers an LOS fault. It officially declares itself blind.
5 microseconds. The speed at which these systems operate is just staggering. Okay, that's LOS. What about DOS?
DOS is degradation of signal. This brings us back to the noise and asymmetry we were discussing.
Where the foghorn ruins the whisper.
Right. Let's say the noise doesn't completely kill the signal, but it distorts it. If the sine and cosine signals become mismatched in their amplitude by just 5 to 10%, it wreaks havoc on the chip's internal math.
The demodulation algorithm gets totally confused.
The document provides a formula for the error it generates. It says the error is roughly equal to 2a times the sine of 2 theta.
Now, instead of just reading the math, let's look at what that physically means. It means the mathematical error is oscillating at twice the speed of the actual physical rotation.
The physical consequence there is severe. The car's computer looks at that math and believes the heavy metal rotor is vibrating violently back and forth.
When in reality, it isn't vibrating at all.
Exactly. But the motor controller, trying to do its job, attempts to correct this non-existent vibration by firing massive, wildly fluctuating currents into the motor coils.
It basically creates a ghost problem and then tries to fight the ghost.
And fighting that ghost causes severe torque ripples. If you were driving the car, it would feel like the entire powertrain was shuddering violently. You'd completely lose smooth power delivery.
Which is incredibly dangerous if you're trying to navigate, heavy traffic.
Absolutely.
And then there's the third failure mode for the chip. LOT, loss of tracking.
Loss tracking is fascinating because it happens when the car is actually performing at its peak.
Like during hard acceleration.
Exactly. Imagine rapid acceleration combined with a slight hardware delay. The chip has a tracking limit set in its internal registry, usually around 14 degrees.
So the internal phase-locked loop is constantly trying to predict the next position of the rotor to stay synced up.
Like a runner trying to keep pace running alongside a moving car.
That's a great image.
Yeah. And if the car suddenly accelerates so fast that the internal runner just can't keep up, and the gap between the predicted estimated angle and the real physical angle exceeds that 14-degree limit, the loop just snaps.
The chip completely loses its lock.
When that happens, it doesn't just neatly output a 0 or an error code. It spits out completely random, chaotic angle jumps.
So the computer suddenly thinks the rotor is instantly teleporting to entirely different physical positions inside the casing.
Which is, of course, physically impossible, but the software doesn't know that.
Now, I want to pivot to the third root cause outlined in the document, because when I first read it, I literally had to stop and reread it. It's called fretting wear.
Yeah, yes. The micro-enemy.
The text states that the ambient vibration of the motor causes micro movements on the connector pins of just 1 to 200 micrometers. Now, a human hair is about 70 micrometers thick.
Right.
I have to play the skeptic here. How on earth can a physical movement smaller than a human hair cause a catastrophic ASIL D level failure in a heavy piece of machinery?
I get the skepticism, but it highlights the microscopic margins of error in high-performance electronics. You have to consider the environment these connectors live in.
It's pretty harsh.
Very harsh. The electric motor is vibrating continuously, anywhere from 100 to 1,000 hertz. It's an intense, high-frequency shaking.
And there's thermal expansion too, right?
Yes. At the same time, the entire assembly is heating up under load and cooling down when you park. That causes the metal in the connectors to expand and contract. So these tiny metal pins connecting the resolver to the main computer are experiencing constant, relentless micro-movements.
They're just constantly scrubbing against each other.
Like microscopic sandpaper. That scrubbing eventually wears through the protective plating on the pins. These pins are usually coated in gold or tin to prevent corrosion.
But once that mechanical friction exposes the raw base metal underneath, usually copper, that raw metal immediately reacts with the oxygen in the ambient air. It oxidizes.
It rusts. And oxidation is a terrible conductor of electricity.
It basically acts as an insulator.
Exactly. The continuous friction builds up a tiny localized layer of oxidized metal debris right at the exact point of contact. The source is very specific here.
Yeah, it notes that this debris layer causes the contact impedance, the electrical resistance, to spike from a highly conductive level of under 5 milliamps to a massive barrier of over 100 milliamps.
A 20-fold increase in resistance caused by a microscopic pile of rust.
And here's the kicker. Because it's caused by ongoing vibration, that high resistance isn't steady. It violently fluctuates as the pins vibrate.
This leads to microsecond-level signal interruptions. The resolver signal is literally flickering on and off, which instantly triggers the LOS and LOT chip errors we just talked about.
It is wild that something so small can bring down a $100,000 vehicle. Moving along, the fourth dimension of failure, the source details, is metastability, which it refers to as clock desync.
This one feels much more abstract and purely digital compared to, rusting pins.
Right. What is clock desync exactly?
It's a fundamental challenge in complex digital logic design. In this system architecture, you have the main microcontroller unit, the MCU, and you have the resolver to digital converter, the RDC.
Okay.
They both operate based on internal digital clocks. You can think of these clocks as a constant rhythmic electrical pulse ticking away, coordinating all the internal logic. The RDC might be ticking at 8.192 megahertz.
But if the main MCU and the RDC do not share the exact same physical hardware clock source, their ticking will inevitably eventually drift apart.
Right, they lose their shared rhythm. We call this phase sliding. Now imagine the MCU needs to read the current angle data from the RDC. It sends out a sample pulse.
But because the clocks have drifted, there is a statistical probability that the MCU will try to read the data at the precise microsecond that the RDC is in the middle of updating it.
It's like trying to take a crisp photograph of someone, but you hit the shutter button right at the exact moment they're blinking.
You catch them right in the middle of a transition, and the result is blurry.
In digital logic, it's called a setup and hold violation. The tiny memory cells holding the ones and zeros, the flip-flops, require a specific, uninterrupted window of time to settle into a stable state.
And if you interrupt them,
If you interrupt them during that microscopic transition window, they enter a state called metastability. The electrical voltage gets trapped at a level that is neither a clear digital 1 nor a clear digital 0.
so it's suspended in limbo. What does the computer actually see when it reads that?
It reads complete garbage. It pulls a 16-bit angle value that is random nonsense. The software sees an angle jump that defies the laws of physics, and again, the system loses control.
That brings us to the fifth and final root cause in this initial physics breakdown: phase lag and deep magnetic saturation.
This is a big one.
The source focuses on what happens dynamically at 15,000 RPM. This is where the physical speed of the mechanics actually starts to outrun the processing speed of the electronics.
This is where the multi-physics coupling becomes truly complex. At 15,000 RPM, the motor's rotor is completing 250 full revolutions every single second.
Wow.
Now think back to that RC hardware filter we discussed earlier, the one catching the high-frequency noise. That physical filter, combined with the time it takes the MCU to run its digital sampling, creates a fixed time delay.
It takes about 1.5 switching cycles for the position data to travel from the sensor through the filter and into the brain.
Which, in human terms, sounds instantaneous.
Sure, at low speeds it practically is.
But at 15,000 RPM, the rotor is spinning so fast that by the time the computer receives the signal, processes the math, and calculates where the rotor is, the physical rotor has already moved on.
The source states this fixed time delay results in a phase lag of over 15 degrees.
The computer is essentially making decisions based on where the rotor was 15 degrees ago. It's living in the past.
But the physical realities compound the error, right?
Oh, absolutely. To spin a heavy rotor at 15,000 RPM or to produce massive amounts of torque, the inverter has to pump massive electrical current through the stator coils.
And this extreme high current causes the iron cores of the stator and rotor to enter deep magnetic saturation.
Yes, magnetic saturation. Basically, the iron acts like a sponge, and you're pouring magnetic flux into it. Eventually, the sponge is completely full. It physically cannot hold any more magnetic force.
When it reaches that limit, a phenomenon known as the cross-saturation effect dominates. The magnetic inductance inside the motor, the variables L and LQ, drops nonlinearly.
Because the magnetic landscape changes so drastically, it physically shifts the magnetic poles of the motor by another 15 degrees or more.
Wait, I want to make sure I have this straight. You have a 15-degree digital delay from the computer processing, AE, a 15-degree physical shift of the magnetic fields due to saturation.
They compound each other. The whole control algorithm is based on field-oriented control, or FOC.
And FOC relies on an incredibly precise coordinate map to apply the magnetic force at the exact right angle.
When you have a 30-degree total variance, the coordinate map completely breaks down. It no longer maps to physical reality.
The computer tries to push the rotor forward, but because its angle map is completely skewed, it might accidentally pull the rotor backward.
Exactly, which causes massive uncontrolled current spikes and a total catastrophic loss of control.
So, bringing this all together for you, the listener, we have just outlined a terrifying house of cards.
A very precarious one.
Microscopic fretting wear causing rust, thermal drift ruining mathematical symmetry, digital clocks desynchronizing, heavy magnetic saturation, and sit-in switching noise swallowing the signal whole.
It's a lot that can go wrong.
With all of these physical and digital realities working against the system, how does the car's computer actually catch these glitches in real time? How does it intervene before you, the driver, lose control?
Well, the engineers know that all these physical failures are possible, even probable over a long enough timeline. So they engineer a digital immune system that is deeply embedded in the technical architecture.
And the entire goal is to detect any of these anomalies with near-perfect accuracy. They operate under a strict metric called the safety time target, or FTTI.
FTTI. That stands for Fault Tolerant Time Interval.
If I'm reading this right, the target is less than or equal to 60 milliseconds, meaning from the exact microsecond a physical fault occurs, say a pin rusts over, the computer has 60 thousandths of a second to detect the error, confirm it isn't a fluke, and safely shut the massive electrical system down.
That is the window they have to work with. And their first line of defense within that window involves redundant hardware checks and what the source refers to as the envelope.
To achieve an ASIL D rating, you cannot, under any circumstances, rely on a single sensor reading, right?
Never. The system utilizes dual, physically independent analog-to-digital converters, or ADCs. They constantly monitor both the sine and cosine signals to ensure they arrive in perfect synchronicity.
If one signal lags even slightly behind its partner, the system throws a red flag.
But the most elegant and robust check is the mathematical envelope. The digital processor is constantly running a fundamental trigonometric equation on the incoming data. Sine squared theta plus cosine squared theta equals 1.
Good old Pythagoras, a fundamental law of geometry.
It's brilliant because it's unbreakable. No matter what the actual angle of the rotor is, if you square the amplitude of the sine signal and square the amplitude of the cosine signal and add them together, the sum must equal exactly 1.
So if the noise we talked about earlier distorts the signal, or if heat causes the amplitude to drop, that math equation immediately fails.
Right. The sum might equal 0.8, or it might spike to 1.5. The instant that happens, the system definitively knows the incoming signal is physically impossible and therefore corrupted.
The source notes that this one simple constant math check achieves a diagnostic coverage of over 97%. It basically acts as a highly efficient, mathematically pure lie detector for the signal.
It does. But the immune system goes deeper. Let's look at the Dewar-Checker dual-core lock step. I find this concept deeply fascinating.
Me too. It is the absolute backbone of modern automotive functional safety architecture.
Inside the main processor chip, you have a primary core, the Dewar. Its sole job is to run the incredibly complex, highly optimized, field-oriented control algorithms to make the motor spin as efficiently and powerfully as possible.
But sitting right next to it on the silicon is a secondary physically isolated processor core, the checker. I think of it like having two accountants audit a massive corporate ledger, but to make sure they don't make the same mistake, you forbid them from using the same accounting methods.
That is the core philosophy. If the Dewar and the checker both ran the same complex FOC math, a subtle software bug in that formula would affect both of them equally. They would both agree on the wrong answer, and the car would crash.
So the checker core operates completely differently.
It does not run the complex FOC math. It relies on fundamental, unbreakable physical laws, specifically stator flux conservation, to perform a simplified, highly robust independent check.
It observes the raw voltage and current going into the motor and basically asks, based purely on the laws of physics, does the angle the Dewar core is suggesting even make sense?
Exactly. And if the two accountants disagree,
Right, what if they do?
if the Dewar and checker disagree by a predetermined critical threshold, the checker core exercises ultimate veto power. It bypasses the complex software entirely. It triggers a dedicated, hardwired physical path directly to the safety management unit, completely cutting the PWM power signals to the motor in just 100 microseconds.
It just pulls the ripcord. It doesn't ask for permission, it just physically severs the power?
Yep.
But I have to ask about false positives. If the checker core is that sensitive and can pull the plug in 100 microseconds, isn't there a huge risk of false alarms? We just spent 20 minutes talking about all the transient electrical noise bouncing around the system. You don't want your car shutting down on the highway just because you drove over a pothole or under a high-voltage power line and caused a tiny electrical blip?
You're touching on a crucial balance in safety engineering, sensitivity versus availability. This is why the engineers implement dedouncing windows.
Okay, what does that do?
The software utilizes a 3-millisecond sliding time window. It acts as a temporal filter. If the RDC chip throws a tiny microsecond error code, the software catches it, but it essentially says, hold on, let's wait 3 milliseconds to see if this error persists.
It forces the system to take a breath and verify before reacting.
It filters out the transient noise spikes, It guarantees that the system won't overreact and initiate a massive emergency shutdown over a tiny, harmless, momentary glitch.
It ensures that when the safety system does finally trigger, it is responding to a genuine, sustained, catastrophic hardware failure.
Exactly.
Okay, so let's play this out. The system verifies a real failure. The Pythagoras math equation fails, the doer and checker cores severely disagree, and the error persists solidly past the 3-millisecond debounce window. The computer knows, beyond a shadow of a doubt, that the position sensor is dead. What happens next? Do you just yank the power and turn everything off?
You cannot just turn it off. This is a critical safety dynamic. If
Mhm.
the vehicle is traveling at high speeds, the source specifically defines this as anything over 7,200 RPM. Simply opening the circuits and turning off the power switches is incredibly dangerous.
I think most people's instinct would be, if a machine breaks, turn it off. Why is turning it off dangerous?
Because a spinning electric motor is, by definition, also a generator.
Oh, right.
If you are doing 7,200 RPM on the highway and you suddenly turn off the inverter switches, the permanent magnets embedded in the spinning heavy rotor will continue to spin due to the car's physical momentum.
Those spinning magnets will generate a massive amount of voltage, known as back electromotive force, or back EMF.
Yes, this state is known as an uncontrolled generator, or UCG.
And since the circuits are off, where does all that newly generated voltage go?
It has nowhere to go but backward. It surges straight back through the inverter system, into the vehicle's DC bus bar, and directly into the main battery pack.
It creates a catastrophic overvoltage surge. We're talking about a surge powerful enough to literally explode the capacitors, vaporize the power electronics, and cause severe, potentially thermal runaway damage to the battery pack.
Which is obviously not an acceptable safety protocol.
Yeah, blowing up the battery on the highway is a bad day. So if you can't leave it on because the steering algorithm is blind and you can't turn it off because it will blow up the battery, what exactly does the car do?
The car executes a highly coordinated maneuver called a Stepwise Active Short Circuit, or Stepwise ASC. It's a controlled two-phase emergency shutdown that uses the motor's own physical properties to absorb the energy.
Wait, you intentionally short-circuit the motor?
Intentionally and very precisely. In phase 1, which lasts for a strictly timed 1.5 milliseconds, the system references the very last known good angle it received before the failure.
Okay.
It uses that data to short-circuit exactly 2 of the motor's 3 phases. This two-phase short acts as an electrical shock absorber. It suppresses the immediate, violent transient current spike that occurs when you suddenly change the electrical state of a highly energized spinning motor.
It basically cushions the initial blow of the failure.
Yes. Then, immediately after that 1.5 millisecond delay, it transitions into phase 2, a 3-phase lower bridge short circuit. The computer simultaneously commands all 3 of the bottom switches in the inverter bridge to turn on.
This essentially loops the generated power back into the motor coils themselves rather than letting it surge backward to the battery.
Exactly. It traps the destructive energy inside the heavy metal of the motor. The source specifically validates that this maneuver strictly clamps the bus voltage to under 720 volts. It perfectly protects the rest of the vehicle's sensitive electronics from the surge.
That is an incredibly elegant use of physics. But what if you aren't on the highway? What if the sensor dies while you're, pulling out of a parking space at 10 miles an hour?
Speed dictates the physics. At low speeds, defined as under 2,000 RPM, the back EMF voltage generated by the spinning magnets isn't high enough to cause overvoltage damage.
So it doesn't need to trap the energy.
Right, so the system executes the exact opposite strategy. It goes into a freewheeling state. It simply opens all the circuits, shutting off the switches, and lets the motor spin freely.
Why not just do the active short circuit at low speeds too, just to be universally consistent?
Because short-circuiting a motor creates massive electromagnetic braking torque. It fights the rotation. At highway speeds, the sheer physical momentum of a 2-ton car easily overcomes that braking force, so the car just gradually slows down.
But at low speeds.
At low speeds, the car doesn't have enough momentum. If you suddenly short-circuited the motor at 10 miles an hour, it would act like slamming a steel rod into the spokes of a bicycle wheel.
Oh, wow. It could violently lock the wheels, causing the car to skid uncontrollably and potentially cause an accident in a parking lot.
Exactly. So below 2,000 RPM, it just lets the motor coast, allowing the driver to smoothly apply the mechanical brakes and pull over.
The level of situational awareness is profound. I mean, the system has 60 milliseconds to diagnose a microscopic fault, Check the vehicle's velocity, calculate the physics, and choose the exact right electrical maneuver to safely arrest the vehicle's momentum without destroying the battery or locking the tires.
It really is the pinnacle of safety-critical embedded systems.
As amazing as that digital immune system is, relying on an emergency shutdown is still a last resort. If the car has to execute a stepwise ASC on the highway, your road trip is over, the car needs service, and you are having a very bad day.
Very true.
Which leads us to the next massive piece of this puzzle. How do engineers physically redesign the hardware and the software so these complex root causes never manifest in the first place? This is the DFMEA, a design failure mode and effects analysis, the art of proactive design.
Real-time diagnosis is your safety net, but DFMEA is about building a thicker tightrope so you never fall in the first place.
I love that analogy.
And they start by attacking that thermal drift issue we talked about in the RC filter, the problem that ruins the symmetry and converts the noise. The source details a very strict design mandate, labeled DGPCS-HW001. This mandate outright bans the use of standard capacitors in the analog front end.
Because standard components just aren't stable enough. What is the alternative?
The design mandates the exclusive use of Class 1 C0G, also known as NP0, multi-layer ceramic capacitors.
Okay, what makes a Class 1 CRG capacitor so special?
It all comes down to the deep material chemistry. These specific capacitors use a dielectric material based on calcium zirconate.
Most common capacitors will change their capacitance value as they get hot or cold, which, as we discussed, ruins the delicate mathematical symmetry of the noise filter.
But calcium zirconate is remarkably, almost stubbornly stable. Its temperature coefficient is practically zero. Specifically, it fluctuates by only 0 plus or minus 30 parts per million per degree Celsius across an extreme temperature range of -55 to +125 degrees.
So it does not matter if the car is parked outside in an Alaskan winter or being pushed to the limit in Death Valley. These capacitors fundamentally do not change their electrical properties. The symmetry of the filter remains absolutely perfect.
And they have another vital property. They exhibit zero piezoelectric effect.
Ah, the piezoelectric effect. Some of you listening might know that some materials generate an electrical charge when you squeeze or vibrate them. Cheap capacitors can actually act like tiny microphones, picking up the physical vibration of the motor and converting it into electrical noise.
By mandating Class 1 C0G, the engineers use material science to physically engineer the thermal drift and the microphonic vibration noise out of existence from the very start.
That solves the analog filter fragility. Let's look at the metastability issue, the digital clocks drifting apart and causing phase sliding. How do you design that out?
The hardware solution here is wondrously brute force once you identify the root cause.
Brute force how?
Well, in the PCBA layout, the printed circuit board design, the engineers physically force the main MCU and the RDC chip to share the exact same hardware clock line trace on the board. There are no separate crystal oscillators allowed. Both chips are literally wired to listen to the exact same physical electrical heartbeat.
It renders the concept of phase sliding physically impossible. If they share one heartbeat, they can't ever get out of sync. It is simple, but structurally foolproof.
Right.
Now, what about the massive 15-degree phase lag at 15,000 RPM, the physical delay inherent in the hardware filter and processing time?
To combat that delay, they embed an active phase compensation network directly into the physical hardware loop. This is a specialized circuit designed to actively anticipate and offset the RC filter's natural delay.
By tuning this network, they can keep the total hardware delay to under 0.5 degrees, regardless of how fast the motor spins or how hot the ambient temperature gets.
But the hardware isn't the only system fighting that phase lag. The software steps in heavily here as well, with what we can call algorithmic magic.
Software is required because even with perfect hardware compensation, there is still the unavoidable digital processing time of the computer itself.
To solve this, the software relies on a dynamic feed-forward compensation formula. It calculates the current speed of the rotor, the variable omega e, and multiplies it by the known processing delay times.
It's the classic duck hunting analogy. If you know exactly how fast a duck is flying across the sky, and you know exactly how long it takes your bullet to travel through the air, you don't aim your rifle directly at the duck.
You aim ahead of it.
Exactly. You calculate the vectors and you aim at the empty space where the duck will be when the bullet arrives.
That is exactly what the software is doing. It calculates precisely where the rotor will be by the time the electrical control signal actually travels down the wire to reach it. It dynamically adjusts the command angle forward before it even executes the motor control math.
And how do they handle the deep magnetic saturation? The issue where the massive current physically fills the iron core and shifts the magnetic poles by another 15 degrees. You can't just wish that away.
No, you have to map it and mathematically conquer it. The engineering teams use a high-resolution 2D lookup table, or LUT.
In a controlled laboratory setting, they meticulously map out the exact complex magnetic behavior of the motor across every conceivable current level and temperature range.
They encode all this nonlinear inductance data into a massive table baked into the software. As you drive, the software constantly checks the massive current flowing into the motor, cross-references it against the lookup table to find the exact nonlinear drop in inductance, and dynamically corrects the angle mathematically in real time.
The sheer volume of real-time correction happening under the hood is staggering. But let's look at the absolute worst-case scenario. Let's say every single layer of defense fails.
The absolute worst case.
Right. The advanced capacitors fail, the single clock sync breaks, the algorithms fall, or simpler yet, a massive piece of road debris kicks up and physically severs the wire connecting the resolver to the computer. The physical sensor is completely, irrevocably dead. Is there anything the design can do to keep the car moving?
There is. And it represents perhaps the most impressive software achievement detailed in this entire document, the sensorless limp home mode.
A ghost sensor.
That is a great way to think about it. If the physical resolver dies, the system doesn't just give up. A parallel, completely silent software algorithm, which has been running quietly in the background this whole time, instantly takes over control.
It is a highly advanced software observer that can deduce the rotor's exact physical position without relying on any physical position sensor whatsoever.
Right.
But how is it deducing physical position without a sensor?
It employs two different methods depending on the speed. At low speeds, it uses high-frequency injection, or HFI. The inverter purposefully injects a tiny high-frequency voltage ripple signal into the motor coils. It then carefully measures the electrical current ripple that bounces back.
Because the physical rotor is made of highly engineered metal and magnets, its mere physical presence changes the inductance of the surrounding coils slightly as it turns.
By reading those tiny returning ripples, the software can physically feel the position of the rotor.
It is effectively using sonar. It pings the metal with electricity and listens to the echo to map where the rotor is hiding.
And at higher speeds, where HFI becomes less reliable, it seamlessly switches to an ASIL D observer. This is a formidable mathematical model that continuously reconstructs the back EMF voltage generated by the spinning magnets to calculate the angle. It even incorporates a model reference adaptive system, an MRAS.
What does the MRAs do?
It acts as an internal tuning fork. As the motor heats up, its internal resistance changes, which could throw off the ghost sensor's math. The MRAS constantly tracks the changing temperature and resistance, dynamically updating the observer model so the ghost sensor remains perfectly accurate, even if the motor is boiling hot.
And the document notes it can transition control to this ghost sensor in just 5 milliseconds. That is faster than the blink of an eye.
It's seamless.
If this happened on the highway, you would lose some power. The system limits torque to 30% for safety. But you wouldn't lose control, you wouldn't crash. You could safely limp the vehicle off the highway and to a service center. There's one more crucial design control I want to highlight before we move on. It involves 360-degree shielding. The source specifically bans a wiring practice called a pigtail ground connection. Why does the physical geometry of how a ground wire is screwed into the chassis matter so much when dealing with electromagnetic noise?
It's a critical aspect of electromagnetic compatibility. A pigtail connection is an older, cheaper manufacturing technique. You take the braided metal shielding that surrounds a data cable, you twist it all together into a single thick wire pigtail, and you screw that one wire into the chassis ground.
The problem arises with high frequencies, right?
Yes. At the extreme high frequencies generated by those silicon carbide switches we talked about, that tiny pigtail stops acting like a ground wire and begins acting like an antenna.
So instead of safely dumping the electrical noise into the chassis, it accidentally broadcasts it into the cabin, or worse, receives more noise from the environment.
High-frequency noise behaves almost like a fluid. It loves to jump off sharp corners and single-point grounds. So the rigid design mandate totally outlaws pigtails.
It requires the use of high-density shielded twisted pair cable with over 90% braided coverage.
And critically, at the connection interfaces, it mandates a full 360-degree ring metal joint. The braided shield must make continuous, unbroken physical contact entirely around the entire circumference of a connector shell. which then bolts flush against the system's metal casing.
By sealing the entire circumference, it creates a perfect Faraday cage around the delicate signal wires. There is no physical gap, no sharp point, and therefore no antenna for the noise to escape or enter through.
It physically blocks the common mode noise from ever reaching those delicate resolver signals in the first place,
Yeah.
stopping the failure chain reaction before it can even begin.
So we have a mathematically perfect, heavily shielded, deeply redundant system on paper. The blueprints are bulletproof.
On paper, yeah.
But blueprints don't build cars. People and machines build cars. And none of that brilliant design matters the second a tired worker on an assembly line crimps a wire slightly too hard or forgets to tighten a bolt. How do you control the physical manufacturing process to ensure this ASIL D system is built flawlessly every single time? This brings us to the PFMEA, the process failure mode, and effects analysis.
Human error is the ultimate wildcard in any engineering system. So the manufacturing process for these specific critical components relies entirely on automated poka-yoke. Poka-yoke is a Japanese manufacturing concept that translates to mistake-proofing.
First, they tackle the delicate wire connections we just discussed. The source document strictly bans any manual wire stripping or manual crimping for these resolver cables.
No, you aren't allowed to have a technician with hand tools anywhere near these cables.
Absolutely not. They utilize fully automated, highly specialized tooling that strips the insulation and crimps that 360-degree shield in one fluid motion.
But the true genius isn't just that the machine does it. It's that the machine meticulously monitors how it does it. These automated presses use a closed-loop force displacement curve monitoring system.
It is measuring exactly how hard the metal press pushes and exactly how far the copper bends in real time.
It is constantly comparing the physical pressure curve of every single crimp against an ideal, mathematically perfect signature curve stored in its memory.
If a single microscopic wire strand is out of place, or if the metal connector from the supplier is even a fraction of a millimeter too thick, the physical force curve will deviate from perfection.
The machine senses this anomaly instantly, aborts the cycle, and physically locks itself down. It will not release the defective part until a quality supervisor physically intervenes, completely preventing a bad crimp from quietly moving down the line.
That is ruthless quality control. Now,
Yeah.
what about the most surprising root cause we covered earlier? The fretting wear. The microscopic rust building up on the connector pins due to engine vibration.
Yes.
There is a deeply involved process outlined here to prevent that, involving high-tech grease and ultraviolet black lights. It reads like a forensic crime scene investigation happening right on the factory floor.
It is a phenomenal process. To prevent that microfriction and subsequent oxidation, the assembly line uses an automated robotic dispenser to precisely inject a microscopic drop of a highly specialized automotive-grade anti-fretting grease directly into the female side of the connector.
The source actually names the compound Niagel 760G. It is a fluorosilicone base with unique conductive properties designed specifically to lubricate the pins and physically seal out ambient oxygen.
Because if oxygen can't reach the raw metal, oxidation cannot occur. No rust, no resistance spike.
But the manufacturing challenge is verification. How do you guarantee on an assembly line producing thousands of parts a day that a tiny invisible drop of clear grease actually coated the entire circumference of the pin perfectly? You cannot trust a human operator to visually inspect it.
They would go cross-eyed trying to verify thousands of microscopic grease applications.
So the process engineers mix a UV fluorescent tracer dye directly into the Niagel grease formula. After the robotic arm injects the grease, the part is conveyed under an automated optical inspection or AOI system.
The AOI hits the connector with a powerful ultraviolet black light. High-resolution cameras analyze the glowing pattern of the grease.
If the vision system does not see exactly 100% fluorescent coverage around the pin, if there is even a microscopic dark spot indicating a dry patch, it rejects the part. It literally locks the holding fixture so the part physically cannot proceed to the next station.
They're using glowing tracer dye to guarantee the invisible rust prevention is flawlessly applied. That is next-level manufacturing.
Now, moving from the tiny, delicate pins to the massive power cables, the text details controls for the main bus bars, utilizing smart screwdrivers and OCR.
The main power bus bars carry massive continuous electrical currents. If the thick bolts holding them together aren't perfectly uniformly tight, the contact resistance increases.
When you push hundreds of amps through a high-resistance joint, you create severe joule heating. It can easily generate enough heat to melt the entire plastic assembly and start a fire.
So before an operator is even allowed to pick up a bolt, an optical character recognition, or OCR, Camera scans the physical packaging the bolts arrived in. It verifies that the batch has the exact correct phosphate-coated surface finish, which dictates the friction coefficient of the threads.
The camera is reading the supplier label to make sure nobody accidentally loaded the wrong box of bolts into the station.
Once the correct bolt is verified, they use highly advanced servo-controlled screwdrivers utilizing the torque angle method. Standard torque wrenches just tighten until they hit a certain resistance threshold.
But a bolt might feel tight simply because the threads are dirty or cross-threaded, leaving the actual joint loose.
Exactly.
Yeah.
The torque angle method tightens to a specific initial snug torque and then measures the exact physical angle of rotation from that point onward. It is monitoring the friction of the threads dynamically in real time.
If the torque spikes too early in the rotation, the tool knows the bolt is cross-threaded or the friction is wrong. It immediately stops the line, ensuring the final physical clamping force is perfect and the contact resistance is always strictly under 5 millions.
Every single physical connection is mathematically verified as it happens. Which brings us to the final, ultimate manufacturing control, which acts as the last line of defense before the controller leaves the factory. The cloud-locked MES, or Manufacturing Execution System.
This sounds like the final boss of the assembly line.
It acts as the ultimate digital gatekeeper. At the end of line, or EOL testing station, the motor controller is fully assembled and powered up for the first time. But before it can be boxed and shipped to the vehicle assembly plant, it has to learn the exact physical zero point of its specific paired resolver.
Because of manufacturing stack-up tolerances, no two physical motors are microscopically identical. So the software has to inject a high-frequency signal, calibrate its internal offset, and learn its unique mechanical zero position.
The document refers to this as Resolver Offset Learning, or ROL. The automated test band runs this calibration routine. But here is the critical failsafe. The testing machine is deeply directly connected to the factory's overarching MES cloud database.
When the machine finishes the complex calibration, it attempts to upload that perfectly calibrated offset value to the cloud.
And what happens if it fails? Say the network drops for a second, or the calibrated value is slightly outside the acceptable tolerance range.
If the overarching cloud database does not receive and mathematically verify a perfectly valid offset value, the MES system completely locks down that specific unit's digital work order. It physically refuses to print the final shipping barcode label.
Wow. Without that specific barcode, the part literally cannot be scanned onto a shipping pallet.
It makes a testing escape literally impossible. A human being, no matter how rushed or well-intentioned, cannot accidentally bypass a failed test because the cloud simply will not give them the physical barcode required to let the part leave the building.
It completely removes the potential for human oversight from the final validation step.
So, let's take a breath and review where we stand. The architectural design is mathematically perfect and heavily redundant. The physical manufacturing process is locked down with UV-traced grease, laser-guided crimping, and cloud-based testing gates.
It sounds foolproof.
But before a major automotive company will actually commit billions of dollars to mass producing this system and putting it into consumers' hands, they have to prove that this hardware can survive a literal nightmare. They have to put it through the ultimate torture test to prove the theory matches reality. This is the DVP&R, the Design Verification Plan and Report.
It is the crucible. This is where they take all that beautiful, pristine engineering and attempt to violently destroy it in a laboratory setting to see if it holds up to its ASIL D rating.
And the first test protocol is appropriately titled Multiphysics Hell. What exactly do they subject these controllers to?
They place the newly assembled, pristine motor controller into a massive, highly specialized composite environmental chamber. First, they attack it thermally. They cycle the ambient temperature violently from negative 40 degrees Celsius up to positive 125 degrees Celsius, back and forth, rapidly.
That's negative 40 to 257 degrees Fahrenheit, shifting from blistering Arctic cold to boiling desert heat.
While it is trapped in that chamber experiencing extreme thermal shock, they attach it to a hydraulic vibration rig conforming to the rigorous VDA 320 automotive standard.
Yep.
They shake the heavy unit violently on 3 different axes simultaneously at an acceleration of 35 meters per second squared.
That is over 3.5 Gs of constant, violent, random vibration while simultaneously boiling and freezing it.
And while all of that physical torture is happening, they power it up electrically. They run the internal silicon carbide power semiconductors at their absolute maximum power output and highest possible switching frequency to purposefully generate the maximum amount of that nasty DVDT electrical noise we talked about at the very beginning.
So they're subjecting it to extreme temperature swings, extreme physical violence, and extreme internal electrical interference, all at the exact same time. It is a simulated worst-case scenario. What is the standard to actually pass this test?
Under all of that combined stress, the system must maintain a pristine signal-to-noise ratio of greater than or equal to 48 decibels. The symmetrical filters must completely suppress the common mode noise, keeping differential noise under a minuscule 15 millivolts.
The final steady-state angle calculation error cannot drift by more than 1.2 degrees from reality. And crucially, throughout this entire multi-physics hell, the system is permitted exactly 0 false LOT or DOS failure alarms.
Not a single false alarm is allowed while the machine is being shaken to death. That is an incredibly rigorous baseline.
But what about our old enemy, fretting wear? The microscopic rust on the pins. There is a test specifically for that, outlining a fretting wear endurance protocol.
For this specific vulnerability, they utilize a grueling standard called LV214SG4. It is a severe, high-frequency vibration profile designed specifically to simulate a decade's worth of intense motor vibration concentrated onto those tiny connectors.
They shake the connector assembly at that same 35 meters per second squared, while simultaneously subjecting it to extreme thermal shock cycles continuously for 300 straight hours.
That is almost 2 solid weeks of uninterrupted, violent shaking.
And throughout those entire 300 hours, a highly sensitive dynamic impedance analyzer is constantly running a current through the pins, monitoring their electrical resistance. To pass the test, the contact resistance can grow by no more than 1.2 milliamps from its starting point.
1.2 milliamps. The margin of error is basically non-existent.
It gets even tighter. During the entire 2-week endurance run, there must be exactly 0 micro-interruptions lasting longer than a single microsecond. If the electrical signal drops out for 1 millionth of a second in 2 weeks, the design fails.
And to prove it wasn't just a lucky fluke, after the 300 hours are up, they actually slice the physical connectors open and put them under an electron microscope.
Destructive physical analysis, doing an autopsy on the hardware.
The microscopic autopsy must conclusively prove that the violent friction did not wear through the protective gold or tin layer, and there's absolute 0 oxidation present on the base metal. The UV-traced fluorosilicone grease has to have protected the metal perfectly for the entire duration.
Okay, so the physical hardware is proving to survive the shaking and the heat. But what about the complex software? How do they rigorously test that stepwise ASC emergency shutdown maneuver we talked about? You can't just intentionally crash a real car on a test track 1,000 times to see if the software works.
No, that would be incredibly dangerous, prohibitively expensive, and scientifically unrepeatable. So they rely on hardware-in-the-loop or HIL fault injection testing.
They take the actual physical motor controller computer, the brain, and plug its inputs and outputs into a massive, highly advanced FPGA simulator.
A supercomputer pretending to be the rest of the car in the real world.
And the supercomputer simulator uses high-fidelity, finite element analysis flux maps to perfectly replicate the complex electrical and magnetic behavior of the motor in real time.
They boot up the simulation and run the virtual motor at the absolute most extreme scenario physically possible, spinning at 12,000 RPM at full braking load, generating massive amounts of energy.
So the computer brain genuinely believes it's flying down the Autobahn, hitting the brakes hard at 12,000 RPM. And then what do the engineers do?
And then the test engineers maliciously inject catastrophic faults directly into the data stream. They will simulate instantly ripping the resolver wire completely out of the socket, or they will inject a sudden, mathematically impossible 180-degree phase shift into the angle data.
They essentially simulate the absolute worst-case physical failures instantly, without warning. They just pull the digital rug right out from under the computer while it thinks it's driving.
And the standard for passing is absolute. The checker core must catch the fake failure and make the unilateral decision to shut down in under 60 milliseconds. It must flawlessly execute the timing of the stepwise active short circuit.
The simulator monitors the virtual physics and must confirm that the maneuver successfully clamped the DC bus voltage to under 720 volts, ensuring the virtual battery didn't explode.
It must also prove it limited the violent short-circuit current spike to under 550 amps, so the virtual wires wouldn't melt.
And it does all this rapidly inside the simulation, proving the software logic is robust and executes flawlessly under extreme duress.
And as a final check, it has to prove it can seamlessly transition into that sensorless limp home mode, the ghost sensor, without causing a crash.
The simulator meticulously checks the virtual torque output during the 5-millisecond handover. The transition must happen so smoothly that the physical torque ripple, the actual shudder that would be felt by the tires on the road, is less than 5 Newton meters.
So if this catastrophic failure happened to you on the highway, you wouldn't even feel a bump. The car would just smoothly dial back the power, switch to the ghost sensor, and keep driving safely.
It thoroughly validates every single layer of the massive ASIL D architecture we've discussed today. Let's step back and look at the incredible journey we just took. We started by unpacking the deep physics of how a resolver failure actually happens.
We looked at how high-frequency silicon carbide noise, thermal drift ruining filters, microscopic rust from vibration, digital clock desynchronization, and massive magnetic saturation can all conspire to blind an electric vehicle at highway speeds.
We then explored the real-time digital immune system designed to catch those failures. We discussed the mathematical envelope checks using Pythagoras, the brilliantly paranoid dual-core doer-checker lockstep, and the elegantly orchestrated stepwise active short circuit that safely absorbs the motor's chaotic energy without destroying the battery.
From there, we looked at how engineers physically design these flaws out of existence from the ground up. We saw them employing space-age calcium zirconate capacitors, algorithmic feed-forward magic to predict the future, ghost sensor observers that use sonar-like pings, and complete 360-degree shielded cables to create Faraday cages.
We reviewed the unforgiving manufacturing controls necessary to build it perfectly at scale. Closed-loop laser-guided crimping that checks its own force, UV-traced fluorosilicone grease inspected by blacklights, smart screwdrivers analyzing thread friction, and cloud-locked testing gates that make human error impossible.
And finally, we watched the hardware survive multi-physics hell, enduring weeks of extreme vibration and thermal shock, before the software proved it could catch a catastrophic fault at 12,000 RPM in under 60 milliseconds in a simulated environment.
It really is a profound reminder of the incredible, largely hidden complexity required to keep modern high-performance EVs perfectly safe for you to drive.
It is a monumental engineering achievement. And as we wrap up, there is one final, incredibly provocative thought buried in the concluding notes of the source material that I want to leave you with.
Oh, what's that?
We spent a good amount of time talking about that emergency stepwise active short circuit, how it elegantly saves the battery by purposefully shorting the motor coils and trapping the energy. But what actually happens to the physical rare earth permanent magnets embedded inside the rotor when that massive short circuit current hits them while spinning at 12,000 RPM?
When you slam hundreds of amps of current into a magnetic field, you generate a massive amount of heat.
You generate a violent spike in temperature and opposing electromagnetic force. The source material hints at the existence of a completely separate, highly advanced dynamic transient mathematical model used solely to understand this phenomena.
It revolves around a concept called the armature time constant. It is essentially a delicate mathematical ratio balancing the motor's internal inductance, its ability to store magnetic energy against its pure electrical resistance.
So balancing the energy trap against the heat it generates. This complex model is used to calculate the exact razor-thin threshold where the sudden violent spike in heat and current from the emergency short-circuit maneuver could cross a line and permanently demagnetize the motor's permanent magnets.
Meaning, the very safety maneuver designed to save your life and save the battery could, if not perfectly calibrated, completely destroy the motor from the inside out in a fraction of a second.
It hints at a whole other layer of invisible thermal safety boundaries, a delicate, high-stakes balancing act of physics just waiting to be explored in another deep dive.
A perfect cliffhanger to end on. From microscopic rust causing the failure to the massive physics equations required to safely shut it all down without melting the magnets. Thank you for joining us as we took this deep dive into the absolute cutting edge of automotive safety engineering. Until next time, keep questioning how the hidden world around you really works.